Okay, so the object of today's presentation is the IVP model. So IVP standing for Implied Volatility Surface Parameterization. And we will be applying that specific new mathematical model to statistical arbitrage and risk management, which are two areas of quant finance which are sort of quite in demand at the moment. So let's begin. So for any kind of new mathematical model applied to finance, one of the most important feature to define first is the model performance criteria that we will take a look at next. So a good mathematical model, especially when it comes to the volatility surface, is that it has to be asset class polyvalent. So that means that whether you're in equities, in commodities, in FX, or in rates, the same model should ideally be able to work with all of these asset classes. It should be function polyvalent, so that means whether you're in risk, in trading, or in other departments within the bank, or the financial institution in general, then the model should be the same. Okay, it's not. I mean, it sounds quite obvious, but if you start working in the financial industry, you'll realize very soon that some of these systems don't always talk efficiently to each other. The third point is dimensionality. So as we will see, the implied volatility surface is a continuous geometrical structure with infinite dimension. So this is obviously not something that we would like to see. So we will talk about how to limit the number of risk factors such that they're not limiting per se. We will also discuss whether and how the volatility surface should be able to handle arbitrages. And we will also talk about liquidity, so liquidity here and FRTB in general. So if you've been working in the financial industry, FRTB is somewhat a new scheme that has been launched or encouraged by the government, which has all sorts of properties which are essentially associated to creating risk systems which are a little bit more up to speed. FRTB standing for Fundamental Review of the Trading Book. One of these properties is liquidity, so we will talk about how the implied volatility model addresses that specific point. And it should be something easily calibratable, and ideally it should enhance models that have already been built in the industry in an elegant fashion, ideally. So here are our model performance criteria. Let's now remind ourselves of some of the market conventions. So hopefully if you're watching this video, you are not a beginner in quantitative finance. So this is the celebrated Black-Scholes model, which you have all seen many, many times. If you work in FX, you are probably more familiar with this version of the Black-Scholes model, which is essentially an adjustment to FX to sort of the risk-free rate here and here, substituted with respect to the domestic rate and the foreign rate. And if you work in interest rates, especially in the last year, you might have become familiar with sort of the bizarre world of interest rates, especially last year. You've been able to witness negative interest rates. So essentially, if you witness this, that specific Black-Scholes model with the log normal assumption doesn't work anymore. So you have to be able to come up with something very similar, but which would be able to accommodate negative sort of prices or negative interest rates in this case. And this is where the normal diffusion assumption comes into play. So this one is essentially the mirror of this one, but using the normal assumption versus the log normal assumption. Okay? So let's now take a look at, so if we go back, sorry. So the object of today's lecture is that specific object. Let me erase this stuff and then use a little bit of color to be a little bit fancy. So the object of today's lecture is this guy here, okay? So the implied volatility that appears in few places in these different formulas, okay? So how can we get and study that specific mathematical structure with respect to the prices that we observe in the market? So these are the prices that we see from the market. How do you get from here to here? So if you're a quantitative analyst, which have worked within this area, you're familiar with the next slide. However, it's good to make a nice reminder for the beginners. So if you've been working in the financial industry for a while, and especially with implied volatility surface, you are familiar with these three methodologies. So bisection method, Newton-Raphson method, and the Brent algorithm. However, we will illustrate what each of these algorithms are doing. So in this axis, you have the price as defined by the different pricing methodologies that we've seen in the previous slide. And you have minus the Black-Scholes of sigma. So this here, you can substitute this with the three different pricing methodologies we've seen before. On this axis, you have sigma, and you are plotting essentially that function here. All right. Let's make it strictly decreasing to make it a little bit more realistic. So in this algorithm, you have an upper boundary and a lower boundary here. So you make initially an educated guess of where these two things should be. So let's say this is sigma plus and this is sigma minus of your initial guesses. So your initial guess, let's say, is somewhere in the middle here, right? Let's say that happens to be here. You try and see whether P minus that entity is positive or negative. If it's positive, you bring this guy right here, and again take the middle of these 2 points right here, and you see whether it's positive or negative. In this case, it's negative, so you bring back this guy here. So you have sigma plus here, and then eventually you will see that you converge towards the right solution. So the solution in which P equals your pricer. Okay? So this is for the Brent algorithm. The Newton-Raphson is sort of similar in a sense that instead of taking midpoints here, you take the derivative. And the advantage of that one is that it is much faster, but sometimes it doesn't converge. So you have the Brent algorithm that intervenes in this situation, which essentially is the Newton-Raphson. And if it doesn't converge, then you switch back to the bisection methodology. Okay? So this is how you fetch that sigma from the price risk. Okay? So this should be sort of well known for people who work again in that industry. And eventually you can map the price matrix onto the implied volatility sort of matrix. So with increasing strikes and increasing tenors. And if you were to plot this person or this guy here, you would see something like this. Okay, so you have increasing tenors here, you have increasing log moneyness here, and in this arc here you have the implied volatility surface. Okay, so it's a nice little feature. You can note that it's not flat. So again, if you're working in finance, you already know why. So the reason why this is not a flat vol surface instead of being that structure is because the essentially the Black-Scholes model is incomplete, and that shape here reflects essentially the limitation of the Black-Scholes model perceived by the traders. Okay, so if you are in equities, if you were to take some sort of trench, like that specific trench here, or that specific trench there, in equities you would see usually something like this. Okay, if you are in commodities, so this is equities. If you are in commodities, sorry, my handwriting is terrible, but if you're in commodities except oil, you have something which is sort of the opposite, so you have something like that. Okay, the reason why you have these different structures, so for the sake of making it a little bit more intuitive, I'm going to vulgarize a little bit these shapes so that it becomes a little bit more intuitive. So in equities, let's say it's something like this. And in commodities, it's something like that, except oil again. Okay, so in equities, this side is bigger than this side. Okay, and in commodities, this side is bigger than this side. Okay, so this is because in commodities, people are afraid of prices going up, so they have a tendency to prefer that side of the implied vol. And in equities, people want to hedge themselves with respect to bankruptcies, and they prefer this side of the implied vol. Okay. All right. So just to make it a little bit more rigorous, so you have sigma here, and in here you have log of that. Okay. All right. So as we have seen, that specific matrix that we've discussed can have an infinite dimension. So how can we define smart risk factors such that you capture the essence of the volatility surface, but at the same time have a very reasonable number of risk factors so that you can actually do something about it? And we will also discuss liquidity and how how arbitrage freeness can be checked when you have an object like this. Okay. All right. So now we've seen in that section here, in the model performance criteria, that your mathematical model should build ideally on something that has been already built and people are familiar with in the industry. And this is exactly the case with the SVI model. So we will recall what the SVI model is if you're not familiar with it. Next, so the SVI model was a model developed by Jim Gatterall in the early 2000s. And that's absolutely a great introductory implied parameterization, which has all sorts of great properties, but the problem is that it's a parsimonious model, so it doesn't really capture some critical risk factors, and it's one of the reasons why it was made obsolete in Bank of America around 20 years or 15 years ago. But if you're not familiar with it, so the intuition with respect to that sort of volatility surface is that so you start with a function which should look like a V shape, right? And the best kind of function that models this is f of x equals absolute value of x, or you could actually write it as square root of x squared. And but the problem is that, as we've seen in the previous slide, whether you're in equities, in commodities, that side should be bigger than this side and vice versa. So you want to be able to rotate that around this axis. So the way to adjust this is to add some sort of linear function here. All right. So you would have, if you were to rewrite that function, you would have f of x equals to sort of b absolute value of x plus, let's say, just change a bit of color just for the sake of fun, rho of x. Okay, so rho being the slope of this, and that allows you, if you were to add this to this guy, you can intuitively see that it starts rotating, but it's not enough. You want to be able to move up the at the money such that it's not equal to 0, so you can actually add, you know, an a here. Okay, and what you have right here is the skeleton of the SVI model. So you have the at the money right here. It's not exactly the at the money, but as an introductory, it's good to think of this as the at the money, B the vol of vol, and rho the skew. Okay. So let's now talk about how the SVI and the IVP are related to each other. So essentially, in blue here, so you have a set of 5 parameters per tranche or per tenor for the SVI, and the IVP essentially completes these 5 parameters by adding these other parameters in red. So this is the IVP model, and this is the SVI model right here in blue. Okay. But for the sake of creating a bit of jargon immediately, so let's say that A here is sort of the vertical displacement. B is sometimes called the vol of vol, or the angle between the left and the right asymptotes. The rho parameter here is usually called the skew, but sometimes also called the orientation of the graph. M is the horizontal displacement, sigma is the vertex, the smoothness of the vertex, so it's different than the implied vol itself, right? It's a bit of an unfortunate choice of parameter here. Nevertheless, since this was the sort of the naming that Gatherall used for the SVI, we kept it for the IVP, okay? Here you have the downside transform. So the downside transform addresses one of the main limitations of the SVI model, which is that in the wings, the implied volatility surface should not be linear in variance space, but should be sublinear. Okay, and that's one of the reasons why the SVI was initially made obsolete in Bank of America, precisely for this specific reason. Then you have in here a few liquidity-related parameters. So you have the at the money bid-ask sort of adjustment, which can be a function or a variable. And similarly, the wing adjustment, same. So it can be either a variable or a function. And in here, here you have a couple of elasticity kind of liquidity related parameters that we will discuss. And P here is the position size. Okay? So how does that visually translate into a graph? So if this is implied vol, so I apologize for the choice of that specific axis. It would have been better to call that variance instead of implied vol. However, I kept it this way because sometimes there is a bit of confusion in the industry between these two things, and geometrically sometimes it can also be confusing. So I kept it as implied vol instead of variance. So the A parameter here in blue, so an increase in the A parameter shifts the whole implied vol in this manner. So that's for the A parameters in the SVI and in the IVP. The B parameter here, which is also known as the vol of vol, is a parameter which increases the volatility when B increases in the wings, all right? You have the skew. So the skew refers to that kind of movement, so a rotation around the axis. M here is the horizontal displacement. And the sigma here, which smooths out the vertex here, acts in that fashion. So this is the reason why I said it's a bit confusing, because most of the time the variance or the implied vol uses sigma as the naming, and however it's also still sigma here for the smoothness parameter. So, but we still kept it this way because that's how Jim Gatterall wanted the SVI to appear. And by the way, I take this opportunity to talk about what the raw here means. So there's different versions of the SVI. So you have the raw SVI, but you also have the natural SVI. Depending on where you work, which kind of functions you work, you may like different versions of the SVI. So usually traders prefer the natural SVI, and people in risk prefer the raw SVI because it's much easier to understand the risk factors this way. I use the raw SVI as a natural SVI because I find it a bit more intuitive to use that, especially because of some of the geometrical property of the raw SVI, which risk factors are more orthogonal than the natural SVI. So we've used the raw SVI here, and every time we talk about the SVI in that presentation, we talk about the raw SVI. Okay? But there are very simple functions that allow you to move from the natural SVI to the raw SVI, and I invite you to take a look at the literature if you really are interested in that kind of transforms. Okay? So now let's talk about the original IVP parameters. So the first one of these, so we talked about the downside transform, so we're going to be discussing next these parameters here. So let's take a look at the IVP formula itself. So again, if you have worked with the SVI, you're hopefully familiar with this guy here, right? With the difference that there's a change of variable here, which you might not be familiar with. And the second thing to notice is that the IVP model has three different sort of set of equations which represent the bid ask. So you have in here, you can see a plus here. I apologize. It's a bit difficult to use that tool. And you have in here the second side of the bid ask equation. All right, so this is the mid, and this is the ask, and this is the bid. Okay, and you can notice as well that for each of the bid asks as well, you have a new change of variable. Okay, this one is this, and this one refers to this one. Okay, and these functions as well refers to, so for these two refers to this one, and that change of variable psi corresponds to this one. It's a lot of information. We'll go into all of these step by step, but I wanted to provide a general structure of that specific parameterization for you not to be, I guess, too bombarded with information too early. Okay. So first, let's talk about the downside transform. So the downside transform again states that, so this is in implied vol space. So invariant space, it would have been much easier to see it. So if I was actually to plot this invariant space, if this is, I guess, what the SVI model would look like, so this would be variance. I would put a square here. The IVP model in a variance space would look like something like that. Okay? So you have that parameter beta in here that allows you to control the dampening of the wings, so that you're still able to capture the limitations of the Black-Scholes model, especially around the at the money. But as you get further and further into the in the money or out of the money, your wings are dampening. Okay, and this is controlled by that specific change of variable. Okay, so this is in sigma space, and this is in variance space. And notice that in the implied vol space, there's already a little bit of curvature, so it can be a little bit confusing when you take a look at this one with the vol of vol parameter that we've talked about later, like before. Okay. So this is what the downside I can't spell. Downside transform is doing. Okay?